So in section 5.4, we'll continue to look at systems of equations, but we will incorporate what are called nonlinear systems, nonlinear equations, giving us a nonlinear system, being where at least one, if not both of the equations, has a variable to a power. It's as simple as that. Linear equations where only our variables with exponents of ones. As soon as a squared or higher shows up, we're dealing with a nonlinear system. Now the processes that we were using before, the substitution and the elimination, or also called addition, methods, really still do apply here. There's a small tweak to them, but really nothing that changes how they work. So just jumping in and taking a look at a couple examples. So we want to solve this first system using the substitution method. So remember, substitution means solve one of your equations for one of your variables, substitute it into the other. I'm going to go ahead and utilize what is here a linear equation, 3x minus y equals 9, and I'm going to go ahead and just move the 9 this way and the y that way. So subtract the 9 over here, add the y over there, simple enough to get y solved for. Now that'll be my expression that I will substitute into my other equation. So x squared equals 2, but now in place of that y, we're putting 3x minus 9, and then plus 10. So that equation with that substituted in, and then we will look at what the resulting equation looks like. Notice it is a quadratic equation. X squared is its highest power. So general approach to these is get everything to one side and factor. So let's see if that works. Also here I'll have a negative 18 plus 10 will be a negative 8, but moving it over to the other side would make it a positive 8. So I'll do that there in that one step. So then the question of factoring this, GCF is 1, two numbers that multiply to positive 8, add to negative 6 would be a negative 2 and a negative 4. So we can factor this with x minus 2 and x minus 4. So what that means, we get two equations. So we get x equals 2 and x equals 4. Now, we need to use these values to find the compared or the paired up y values to them. And notice the important part here. If we went back up to this one, actually let's go to the linear one, and we'll just stick with the linear equation. We're just going to stick with the one that we know the points would exist for. So if I'm checking x equals 2, subtract the 6, looks like x equals 2 pairs with y equals negative 3. So we get to point 2, negative 3. Oops, that's off the screen. And then using x equals 4, looks like we get y equals positive 3. So the point 4, 3. So we do end up with two different solutions, 2 points where these two graphs, I should say, intersect. Just to now kind of talk about them in summary, we should recognize this is a line, right? A linear equation would be a graph of a line somewhere. And this graph being an x squared, right? Y and an x squared, this is a parabola. And so there's lots of ways you could imagine that a parabola, like the curved U shape, and a line could intersect at 2 different points. So it does make sense that we're getting 2 different solutions here. All right, let's take a look at the next one here. It does again say use substitution, so we'll utilize this very simple linear equation up here. So if that's our equation, all I have to do is move the y over, and it's, oops. It should be y plus 3. Add the y over, and we've solved for x. So now I will substitute this x in. So we'll have y plus 3 minus 2 squared, and then the rest of that will be the same. So again, just replacing this x with that y plus 3, giving us that equation. I'll I'll go ahead and simplify that first, definitely. Now, we have to multiply out each of these. Make sure you remember that this is a y plus 1 times y plus 1. That's a y plus 3 times y plus 3. Don't make the common mistake of just squaring each term, but think about multiplying it out, and you get y squared, y, and 1, y squared, 3y, and 9 from all the multiplication there. And then combining all the like terms, got 2y squared there, y, 3y gives me 8y, 1 and 9 would give me a 10. I do want to also make sure I bring over that 4 though, because again we see we have a quadratic equation, so we're going to try to solve that with factoring z equal to 0. So there is the simplification of it. Factoring, we can see a 2 comes out, so y squared plus 4y plus 3. And again, two numbers that would multiply to 3 add to 4 would be a 1 and a 3. So y plus 1, y plus 3. So we're going to have y plus 1 equals 0, and y plus 3 equals 0. So that gives us two different possible values for y. So here is where we want to mention, with these two values of y, thinking about what you'd find if you went back to either of these equations. So this one here, this is a linear equation, it's a line, right? So we know that there'll be one x value that pairs with each y value, giving us a coordinate point for our y value of -1 and a point for our y value of -3. This equation here, we did get introduced to a long time ago, early in the semester. This is a circle. And so with a circle, one thing we talked about, a circle isn't a function, right? It does not pass the vertical line test. If we were to take those y values and plug them into here, we would get multiple x values. But we don't necessarily want that, because think about where a circle and a line, I'm just going to draw a picture even though this is not the accurate picture. Think about where a circle and a line intersect, right? They intersect at most 2 points, right? One at this y value and one at this y value. But if you plug those y values again into the circle, you're going to get this point and you're going to get the other point that's at that same y value. Same with this one, this y value and this y value. But those are not places where this line crosses, so we don't want those. So that's why, with an example like this, a scenario like this, always go back to what I'll call your simpler, more limited equation or function to find the points that we actually care about, rather than all the points on on either function, on the other function that are at those y values. We want the ones specifically on this simpler line in this case. So I will take this value of y, plug it into our linear equation, and get x equals 2. Same thing there. Get that, and so there are our pairs of 2, -1, and 0, -3.